Mm. So now instead of just the idea is the same. So you have a f, f as a function of z that is analytic over a certain region. Now you and then over this region f is analytic. Then you choose a curve, any curve within this region, it's called C. And now you choose a point within this curve, this closed loop, C sub 0. So f is analytic, but you choose any point C sub 0. Then you consider this integration, f of c. So instead of this f of c dc, you are dividing a factor c minus c sub 0. Okay, and try to evaluate that, and then the formula is that this is just equals to 2 pi I times f sub c, or you want, I think your text divided by 2 pi I. It doesn't matter, this is f value c sub 0. Okay, so that is the Cauchy formula. Okay, now how to prove that? How to prove that? The idea is just like what we did here. Now we keep deforming. This is C. Remember, Z sub 0 is within this C, and then this is the only singularity because F is analytic within the whole region, and the only singularity is at the 0 of the denominator, which is C equals C sub 0. So this is a singularity within the integral. So as long as we deform this curve, not going through the singularity, we are fine. So we keep deforming until we are going to a very small circle around C. So this circle, you can say that this is C minus C sub 0. Let's just write the sequence now. That's too small, so Z. Going through the circle here, this circle is indicated by this formula. So C sub 0 plus a small region, small radius turns into that. So this is a complex number, except that this argument is very small delta. We'll let delta go into 0. Or the other way around is C minus C 0. Delta. That's on the circle, this little circle. We deform C to this circle. And over here, we already showed that the integral will be the same. Like the integral is unchanged as long as we deform it, not going through singularity. So this will be equal to keeping the coefficient in front. Now you're going through this little circle instead of the Z. And now the idea is because delta is so small, so Z is almost like C sub 0. So for a well-behaved function, as long as it doesn't jumping violently at C sub 0, then the F value on this path is almost the same as C sub F value at C sub 0. Okay, and this C minus C sub 0 in here, we already have that. So that's delta e to the I k in here. And DC is coming from here, so DC from here, DC just because C sub 0 and deltas are constant. So this is just like what we did before. So you get the I equal to I e to the I k to d. Okay. Now this is dc, your I theta. Okay, and now we have this is a delta. I forgot. This is delta, or multiply delta. Okay, so delta cancel with delta, e to the I theta cancel with e to the I theta. This I cancel with this I. And f sub 0 is a constant take out from the integrand. Or the f, all is left is integrate c theta from 0 to 0. Which is 2 pi, right? It's just 2 pi and cancel the 2 pi. Okay, so that's the Cauchy integral formula. It's okay, so that's basically very simple because this direct application of this deformation property. So as long as you deform it, now we are using what we set out to do. We deform the curve, original curve C to another curve that is allow us to do the integral more easily. Okay, so that's what we did, and then you evaluate that, and that gives you the exact